Should I just get going now, or should we wait a minute more to give people time to come back from the break?
Well, I think we should get into the practice of starting on time. Otherwise, we will start all the slipping. So,
okay,
why don't you go ahead?
Good. All right. So, welcome everybody to my lecture on trend attribution today. This will be the first. Tomorrow, there's the second. My name is Sebastian Sippel. I work at ETH Zurich in the climate physics group. Thank you for the invitation. It's a pleasure of being here today and talking to you. I wanted to say a few things about this lecture first. So the idea is really to provide an introduction into basically the key concepts of trend detection and attribution, and that's mostly based on key literature in the field, which I intend to provide afterwards to you. But if there's any questions, please don't be shy and just speak up and ask them, because I think that's really the value of being here together. And I also wanted to say to caveat, so 2 hours are quite short, so I'm not sure how far we get, but I will also make available some links to more in-depth topics in case we cannot cover everything in these 2 hours. And the second caveat is that I believe there's a broad variety in backgrounds of students. And so I try to focus really on concepts, and so try to strike a reasonable balance. But this also means that there will be quite very little actual math or statistics. So the hope is that based on these lectures, you'll be able to kind of dig deeper into specifics, like more math or stats topics about detection and attribution in the future. But this will not be the focus in for these 2 hours. All right, now I would like to kind of come to the topics that I hope to cover in these 2 hours. So I would like to kind of provide an introduction into basically a few examples of large-scale changes in the Earth systems, and basically talking a little bit about cause and effect. I know Marlene this week will talk a lot more about causality, and then a little bit also about kind of the physical basis of the greenhouse gas effect and so forth. And then I would like to really come to the kind of what is at the core of the concepts of detection and attribution, and that's basically a separation of a force signal versus internal variability, and kind of trying to explain what this actually is. And then I'll come to kind of the concept and the logic of this trend or long-term detection and attribution that's being used in IPCC reports, for instance. And then this will be tomorrow, hopefully, I will talk about traditional fingerprinting a little bit. So that's the standard approach that IPCC uses for trend detection attribution. And then I would also, if there's time, talk about non-standard approaches that have been kind of used more recently, which is relating to separating dynamical with thermodynamic trends. So a little bit into what Aglaé has just been talking about, but also about basically pattern recognition techniques to separate the signal and the noise. But before all of these, I would like just to give a few examples of how we see the Earth system is changing. And these are all taken from the most recent IPCC report. So as an example, we're seeing that concentrations of well-mixed greenhouse gases, such as CO2 on the top, or methane or N2O, have all been increasing quite a lot over the kind of industrial times. And basically the IPCC has concluded that in 2019, atmospheric CO2 concentrations were higher than at any time in at least the last 2 million years. So here's only shown the last 2,000 years. And there's a high confidence about that statement. And concentrations of methane and N2O were higher than at any time in at least 800,000 years. And while these are kind of greenhouse gases that we can measure, of course, we can also look at kind of climatic responses. So here you see an example for temperature trends. So on the x-axis, you see the temperature trends over kind of the last 40 years, basically to the left globally, and then in the middle for the tropics. And then on the y-axis, you see basically the altitude in the atmosphere. And you're seeing that these temperature trends really indicate on a global or also tropical scale that there's a warming at the surface, and there's a warming throughout the troposphere, basically, but there's a cooling in the stratosphere. So the point I'm trying to make is this is not like we're not seeing kind of random changes occurring at random trends or something like that, but there's really a distinct physical signal that basically there is warming in specific places, such as at the surface, which is probably the most important, but also in the troposphere, but then there's cooling at other places, such as the stratosphere. And I'm not going in this lecture into the physical reasons of that. I'm just saying that these are kind of really distinct signals that are well understood from a physical point of view. And in a very similar way, if you look at basically surface temperature trends, what we're seeing, or what the IPCC is basically putting out here, is that land temperatures, so temperatures over land, have warmed much faster than temperatures over the ocean. So again, we see a very distinct signal in these trends, and again, that's physically very well understood, but it does not mean that everything is kind of changing in the same way or something like that. And as kind of the second to last large-scale Earth system change that I wanted to highlight here is about humidity. So now turning a little bit to the water cycle. So you see at the top, you see basically a map of trends in specific humidity, so the absolute amount of moisture in the air. And what we're seeing in specific humidity is essentially a kind of global increase in humidity, at least everywhere where we have data. And we see this here as a time series as well. However, if we look at a different measure of humidity, namely relative humidity, so not the absolute moisture content, but the relative moisture content, there's no increase, for example, or even a slight decrease. And again, this is just saying that there's a distinct signal. It's physically well understood why there are these increases in specific humidity, but not such increases in relative humidity. And of course, these are kind of this physical understanding about these changes in combination with the observations. This is where basically detection attribution tries to really go and use the physical understanding in the statistical analysis that the detection attribution actually does. As a last point in terms of kind of large scale trends that we are seeing, this is a time series of ocean heat content. And I mean, if we compare this, or if we kind of compare this in our minds to the temperature changes we have seen just 2 slides before, we see that this ocean heat content also shows increases, of course, because the Earth system is taking up heat. However, here's very little variability compared to the temperature increase, and of course that's also something that is very well understood from basic physics. And we'll get into this a little bit in a minute. But so just to sum up this introduction here, so we're seeing that the Earth system is changing. We can measure this, and the IPCC, so the International Panel on Climate Change, in its most recent reports, then highlights basically statements not only about how the observations are changing or what is kind of happening in the observations, but it really also says basically what the causes are. So it says, for example, in its chapter 3, so in the chapter about human influence, it says that it is unequivocal that human influence has warmed the atmosphere, ocean, and land since pre-industrial times, and even more specifically, it is likely, so that's not as certain as unequivocal, that's something to note here, but still it is likely that human influence has contributed to observe large-scale precipitation changes since the mid-20th century. So again, warming is unequivocal, precipitation changes are likely. And as a last statement I wanted to highlight is that human-induced greenhouse gas forcing is the main driver of the observed changes in hot and cold extremes on the global scale. So that's also very certain, and on most continents. So the IPCC basically concludes that it's humans that are kind of basically to blame for the warming, but it's even more specific and saying it's not just kind of something that humans do, but it's really greenhouse gas forcing as the main driver. And now, of course, that's based on detection and attribution. And of course, my main goal for this lecture is to really kind of to get across the concepts of how we know, or how in this case the IPCC knows with confidence about these causes. All right, so this was my introduction about large scale changes. Are there any questions up to now? If so, please speak up, otherwise I will continue. All right, so the second part of my introduction will be a little bit about cause and effect. So, okay, we're now kind of trying to sink into how do we find out about these causes of changes, and kind of maybe the first idea that one could have, very naively, of course, but one might just think, well, we can go and look at correlations. And of course, correlation is not attribution, and I just wanted to kind of to make this very, very clear here. So this issue of cause and effect. So here, this is a little bit a fun example, but it's not a joke. It's really published in a relatively kind of prestigious medicine journal. So this is a correlation of the chocolate consumption per kilogram per year in capita in a bunch of different countries of the world. And on the y-axis, you see the number of Nobel laureates per 10 million population. And you do see a relatively good correlation, but of course we would probably all intuitively somehow think, well, this is not based on some physical relationship between the number of Nobel laureates and the chocolate consumption, but this must be somehow mediated by some confounding effect, such as wealth or something like that. However, this journal kind of makes this probably mistake to really kind of speculate based on this correlation about potential physical hypotheses. So this paper says it seems most likely that in a dose-dependent way, chocolate intake provides the abundant fertile ground needed for the sprouting of Nobel laureates. And then it goes on and says, well, maybe it's not that chocolate intake makes you a Nobel Prize winner, but maybe it's the other way around, that that's what they call reverse causation. That is, that enhanced cognitive performance could stimulate countrywide chocolate consumption must also be considered. However, of course, I just wanted to say, of course, we all know that the correlation is no evidence for one being a direct driver of the other. And again, it seems most likely that a confounding variable that's somehow related to kind of the societal wealth or kind of eating, basically eating habits or something like that is really the causal variable here. But so just saying based on a correlation, you should really never really based on a correlation alone speculate about physical processes going on. And in a similar way, of course, we can. Of course, there's a discussion about CO2 and temperature. So if we look into glacial cycles, and that's something that is also kind of discussed a lot among the climate skeptic community and so on. So if you look at CO2 and temperature and how they correlate with each other, so we see CO2 in blue here and temperature in red here, and this is over the last 800,000 years or so over the main glacial cycles, and we see they are really kind of tightly correlated over these 800,000 years. So it does seem plausible that they are somehow related to each other. And of course, based on physical understanding, we know this. However, there has been this kind of a lot of discussion about this argument that CO2 actually may lag temperatures by a few hundred up to 1,000 years. So there have been studies that say, well, actually CO2 comes, the increase in CO2 comes first, and then temperature comes a few hundred up to 1,000 years later. I mean, this is, by the way, this is being kind of refuted by more recent studies, but in any case, if there would be a lag of the two, this is of course not, this is in some way exactly what we would expect, because there were no humans burning fossil fuels during the last ice ages. So CO2 kind of served as a feedback to orbital changes rather than the climate forcing as it is today. So CO2 was kind of both a cause and an effect of these increased temperatures. So it's really basically impossible based on a kind of lead lag correlation analysis alone to establish the direction of causality because of these well understood physical reasons. CO2 is both a cause and effect, increased temperatures during glacial cycles. So this is just kind of a warning that statistics and exploratory data analysis is really useful, and please do it, but be very careful with the interpretation of these analyses. All right, that was the first, maybe slightly naive way to think about cause and effect with correlations. And of course, maybe another approach to kind of to try to think about the causes of climate change and for the changes we see in climate variables, maybe to look into the physics and talk them and think about the Earth energy budget and its imbalance. So I just wanted to briefly highlight this here. I mean, this is not a lecture about the physics, but I just wanted to say, well, this is kind of a line of evidence that leads to detection and attribution. So of course we do understand, so this is also again a figure from the IPCC report, we do understand the Earth's energy budget. So these are basically radiation fluxes. So the Earth is basically heated up by incoming solar radiation. Parts of these are reflected by the Earth system, and parts of them are basically radiated back into space through basically thermal or long wave radiation. And of course, we know that the greenhouse effect acts on this long wave radiation. So if we basically these numbers here are from satellite measurements, but if we do make the balance, of course, energy has to be preserved, and so there must be it must equal to 0 in the end. However, if we do the numbers here, we actually find that there is a certain imbalance, and this means there's a small but obvious and significant imbalance, meaning that the Earth's system is taking up heat at the moment. That's something that we really can measure with satellites. So we do know the Earth is taking up heat from very basic physical considerations, and we can actually track this Earth energy imbalance and basically track where this additional heat is going. And again, that's from the IPCC. So this energy imbalance, it does result from an increase in greenhouse gases, mostly basically absorbing this long wave radiation. And this is basically leading to increased radiative forcing that leads to this accumulation of energy in the Earth system. And we can actually use basically an energy inventory of where this additional heat is going. And if we do that, we actually see that basically most of this additional energy in the Earth system is going into the ocean. And so if you think about this figure that I showed up at the beginning, this increase in ocean heat content, this may be a good explanation why this increase in ocean heat content is so steady and shows so little variability, because most of the increase in heat actually goes into the ocean. And just as a last point I wanted to make, of course, we can use model simulations and try to basically track which different factors based on basically model calculation about the radiative budget, how this Earth energy imbalance is sustained and which basically forcing agents sustain this Earth energy balance. So as I said, this energy imbalance, it leads to a radiative forcing. So basically this increase in energy input, and because we know the concentration of well-mixed greenhouse gases or CO2 as one part of the well-mixed greenhouse gases, but also things like aerosols or land use changes, we can actually use model calculations to get a first sense of the relative importance of these factors for sustaining basically Earth energy imbalance. And if we do that, we see how basically the total anthropogenic, this is the red line as a time series here, how this radiative forcing due to anthropogenic forcings increases. And we also get a sense that there are some basically forcing factors such as CO2 or other well-mixed greenhouse gases that are basically leading to a strong increase in radiative forcing. But there are also other forcing factors that counteract this increase, such as aerosols mainly. And so the total anthropogenic forcing we see is actually basically a combination or a compensation, or partly basically the increase by greenhouse gases partly offset by the aerosols. Okay, so we know now, based on these kind of very basic physical considerations, that increases in greenhouse gases should lead to increased energy uptake of the Earth, and this is indeed what we see in terms of ocean heat content, for example. And just to sum this up by introduction about these large-scale changes in the Earth systems, we do observe these changes in the Earth system with very distinct trend signals. So we see that land is warming faster than the ocean, that basically the troposphere is warming and the stratosphere is cooling, and things like that are in most cases physically very well understood. We have seen, and I wanted to put this out as a cautionary note, that kind of lead lag or other types of correlation analysis, or even other statistical or exploratory analysis, are really useful to understand the data we're working with, but basically alone, so using them alone cannot reveal the causal directions, and they are not basically the basis of attribution as done by the IPCC, for example. We can of course look into the physics and say Earth energy balance, Earth energy imbalance, apologies, is a key indicator to track these energy flows through the Earth system. And these radiative forcing estimates, they give us a sense of the importance of individual forcing agents over time. But, and again, that's a caveat, this physical understanding is of course crucial, but just because we know that the forcing has changed does not mean that we have detected or attributed changes in the response. And so what I would like to do next is basically to go into these ideas of force signal versus internal variability and these kind of concepts of detection attribution, because they are just an additional line of evidence that basically complements this physical understanding that we do actually expect these changes based on physical considerations alone. But before I do that, I wanted to ask if there's any questions right now. Okay, yeah, so there's one question in the chat. The question is why temperature across the land why the temperature increase over land is more than the temperature increase over water, as mentioned in the presentation. So the physical reason for that is that there's at least two. So the effective heat capacity over land is smaller than over ocean. So the ocean can take up more heat, and that's why it's basically warming up slower. That's one reason. And the other reason is that the ocean basically consists of water, and so it's an infinite reservoir of water to evaporate. So part of the energy that would heat up the ocean can actually go in increased evaporation, whereas over land there's of course also evaporation, but it's somehow limited because soil moisture is not an infinite reservoir of moisture. And so basically these two effects of the different heat capacities and the infinite moisture that goes into evaporation, these are both leading to what we observed, namely that the land is warming up faster than the ocean. I hope that explains the question. And is there?
Hi, Professor. So the absorption rate will play an important role in that question, like the temperature difference across the water. So is it just because the absorption rate is more for the land? Is that one of the solution for that?
So the question was if the absorption rate is a reason. I'm not actually sure if I understand the question correctly. I mean, it's mostly due to the different heat capacity. So in a sense, it's kind of that the ocean warms up as a whole, and so the surface alone is not warming up that fast as the land. Whereas, and the other question, and the other thing is the evaporation differences over the land and the ocean, because that also evaporation is basically an energy flux. So you need energy to evaporate, and so if the ocean can evaporate more, this means, relatively speaking, less energy is going into the warming. But maybe we can kind of continue this discussion later on, such that I can dive into the detection attribution. Okay, so now I would like to to introduce the concept of force signal versus internal variability. And I would like to illustrate this concept with from a seminal paper that Clara Desa published about 10 years ago in Nature Climate Change. And I would like to first invite you to look at these maps to the left. So what Clara Desa is doing, she runs a climate model. So the exact same climate model 45 times into the future for 55-year temperature trends, and she starts this in 2006. So these trends go from 2006 to basically 2060, and she has basically 45 different simulations. So that's called an ensemble of simulations. And the only difference in these simulations is that she starts with different initial conditions. And on average, so as an ensemble average, she arrives at basically this warming over North America. However, if she looks into the warmest simulation, which you see here in the middle left, and the coolest at the bottom left, she actually sees that there's quite a lot of differences between the warmest and the coolest simulations. And again, these differences are not due to the physics, because it's exactly the same model. These differences are only due to what is called internal variability in the climate. And of course, this internal variability in the climate system, you can think of it as kind of random variations in the weather on a daily, weekly, or seasonal timescale. But of course, also these internal variations can persist over many years, and in fact decades. And as she's showing here, for example, if you look at the time series for Seattle, you see, so the black line is basically the observed temperatures up to 26, and then it's basically the model simulation. So in red, the warmest of those 45, and in blue, the coolest of these 45. And you actually see that just based on, so the only differences here is due to internal variability. So you may actually arrive in a very different climate future simply due to differences in internal variability. So this is really an important concept to embrace, that what we are seeing in terms of observed trends is always a combination of the force response, so a component that's basically externally forced, so due to solar forcing, aerosols, or greenhouse gases, plus some internal variability. So that's really a seminal concept, and that's basically also used implicitly basically all the time in detection and attribution. So basically the mental model that people are using is that there's basically a force signal that's predictable, that's modeled in a sense deterministically, and this is basically, and then there's basically some noise that's of course not noise as such, but an atmospheric process, but basically unpredictable, or at least predictable to a small degree from memory, and that's basically modeled probabilistically. And that's a key concept that I would hope that everyone takes away from this lecture. And of course, just as another illustration, if you do the same thing for precipitation, you see that even on relatively large regions such as Southern North America, you still see that even on 55-year timescales, internal variability can still make quite a large difference for the climate future, even though the force response, of course, is always part of these simulations as well. Right, so we can now just look at the global mean surface temperature. So this, okay, sorry, there's no label on the y-axis. This is the time series of global mean surface temperatures from different data sets. So the y-axis is global mean temperature. But of course, if we see, okay, we see a trend here. The trend has increased since about 1970 or so, and there was an early increase from around 1900 to 1945 or so. But of course, it's really hard to decide based on a time series like this, what is actually the signal we're looking at, and what is internal variability. And of course, that would be the goal of detection and attribution, to distinguish these two and to say what are actually the causes for the signal. But in the first place, we have to decide what is actually the signal. And of course, what we always need to have in mind as well is that there could be other problems with the data, such as instrument problems, basically interpolation if we have not measured everywhere, coverage and so forth. So now I would like to go into the separation of the signal and the noise. And again, that's basically a sub part of detection and attribution. And I would like to briefly illustrate different ways how people separate the signal and the noise. So one standard approach, maybe the most simple approach, in order to basically try to get an estimate for the signal from the noise, is just smoothing, using different smoothing methods, trend estimates, low-West filters, and things like that, or higher order polynomials on basically to extract the low frequencies from an observed time series, basically, which kind of implicitly makes the assumption that again, our force signal is basically added plus some noise. And if you're willing to assume that your noise has relatively little low frequency variability, you may just use a low frequency filtering method and then say, well, this is actually my estimate of the force signal. But of course, that's doing this alone is quite dangerous, because there could be decadal variability that's not forced, of course, and you may just alias this into your smoothing estimate of the force response. And of course, this doesn't really tell you yet what the causes are. It just gives you an estimate of the low frequency variability in your time series. But it's something that's being used quite widely in climate science. The other thing you can do, and that's quite popular and that's quite standard in climate science applications, that's mostly being used with model simulations, is if you do have the luxury of an ensemble of climate models, such as the one by Clara Dessa that I just introduced, you can, of course, you can say, well, if I have many members, say if you have these, okay, I go back, if I have these if I have these 45 different simulations, of course, I can compute an average. And of course, because the internal variability is assumed as basically uncorrelated noise that just arises from differences in starting conditions, then I can just use the average in order to filter out internal variability, because that's the random process. So that's a standard way in climate science to say, well, I average over multiple ensemble members to remove the internal variability, because this is the variability that varies between the realizations. And then I arrive at an estimate of the force response as an ensemble average. And this is being done widely with, say, either multi-model simulations such as CMIP, CMIP5 or CMIP6, or kind of even in a more clear sense in these single model large ensembles where you drive the same model many times with different initial conditions. And then, so this is illustrated here. Then you have many members, and the average is then treated as basically the forced or deterministic signal. Okay, there's something going on in the chat. I'll read that later. Okay, and a third way how the signal and noise are being separated, and this is a little bit advanced now. I would like to, if there's time, I would like to talk about this tomorrow a little bit, are these so-called advanced pattern filtering techniques. So this is, for example, there's a paper in Journal of Climate 2 years ago, but it's also the older papers on that as well. And there's a webinar where you find the link here, but hopefully I will have some time to talk about this tomorrow as well. And the idea basically of these techniques is that there are these pattern extraction or pattern recognition techniques basically rooted in statistics, where the idea is, okay, we can actually compute for every grid cell in space, we can compute a signal to noise ratio. And if we do that, we actually see that the signal to noise ratio is quite different across different locations, depending on the variability, and depending on how large the force response is. But we can actually, of course, look at the grid cells, which is not so helpful as such, but we can actually use pattern information. So we can use the information of the information that is in the patterns in order to basically filter out the noise and to basically to gain information about the signal in a pattern way in an ensemble. So that's basically the idea, and I hope to go into detail with that a little bit more tomorrow. And then a fourth way, which we'll look into now a little bit more in detail for the remainder of this lecture, is of course kind of this more or less traditional detection attribution to identify basically a known force response pattern from observation. So in a way to combine the models and the observations. So before I conclude the signal, the signal to noise and force response versus internal variability chapter, I would like to briefly speak about different sources of uncertainty, because this conceptual separation between internal variability and force response can also be used to better understand projections of climate change. And that's, again, a quite seminal paper by Hawkins and Sutton published in BAMS. And it basically looks at future projections. So now we're not dealing with the past. So now we're dealing with basically projections into the future. So you see the lead time here, and basically looking at the uncertainty, the total uncertainty and the fractional uncertainty in simulations by different models. And what we're seeing here is that internal variability, of course, is one part of the uncertainty in the projection, because as I've explained, this is the noise we cannot pin down deterministically. But of course, there are other uncertainties, and this is basically model uncertainty. So if you use different models, of course, this causes an uncertainty as well. And what turns out to be the largest uncertainty far into the future is the scenario uncertainty. So of course, how much greenhouse gases we emit into the atmosphere in the future is going to have a large influence into what the climate outcome is. And so Hawkins and Sutton have quantified these basically different fractional uncertainties over time. And you see this here, and the orange one is the internal variability. And on the left, you see this on the global scale for mean surface air temperature. And on the right, you see this only for the British Isles. And I just wanted to mainly make the point here that this noise of internal variability makes the largest difference in the very near future. Of course, that's kind of obvious, because in the longer term future, the scenario uncertainty is really dominating, because then it really matters how large the greenhouse gas emissions are. Whereas in the near term, this internal variability really makes up a large part of the uncertainty, and it does so even more if you look at more regional scales, because of course at the global scale, variability is smaller than if you look, say, only at a certain region, such as the British Isles. And here we see that internal variability actually makes up something like 30% 70% of the uncertainty in the near future. So to sum up this part of my lecture, what we observe is a combination of force change and this internal and largely unpredictable variability. And the separation of these two, of course, is crucially important, but it's not easy, and you always must make some assumptions about either about the data or about the statistical method. And these signal to noise ratios you can get from that, they really depend on the variable you're looking at. So as I've showed with this comparison between temperature and precipitation from Claradesa's paper, so precipitation has more variability than temperature typically, but it also depends on the spatial scale, as we've just seen from this Hawkins and Sutton example. It depends on the temporal scale and so forth. And as a third takeaway point that I want to make here is that various statistical techniques exist to separate forced responses from internal variability, such as these pattern recognition techniques. It's possible to do this in models, but it's generally, of course, more difficult to do this in observations, because for observations we only have one historical realizations, and we have so we only have one realization, and we have of course, if we go far back in time, we also have some data problems and biases and so forth. All right. Are there any questions now on this second part about force response and internal variability? I don't see anyone speaking up. Then I would just continue with basically the concepts and the logic of detection and attribution. And this is probably the last part that I'm trying to cover today in the last 20 minutes. And then we would have an additional hour tomorrow to talk about basically the technique of the fingerprinting approaches and these non-standard approaches. So what is detection and attribution according to the IPCC or according to kind of country scale national climate assessment? So the typical definition of detection attribution is that it involves assessing the causes of observed changes in the climate system through a systematic comparison of climate models and observations using various statistical methods. So this means that detection attribution is really at the core of basically making a formal or a kind of a systematic comparison of model simulations with observations, and typically using some form of statistical analysis for that. So it's really at the intersection of using models and observations and statistical techniques to come up with that comparison. And so why do we need it? So one thing that's obvious, that's what this lecture is about, is that we need to understand historical climate change and its most likely causes at the global and regional scale. We just need to know this. But there are other reasons why detection attribution can be really useful. One is that it can provide constraints on future projections. So if we better understand the past evolution of climate, we can use the historical climate trends, or let's say the historical trends forced by greenhouse gases or driven by aerosols. So in order to constrain these future model projections by basically retaining the models that have the more realistic evolution of the historical climate. And also we need detection and attribution as a prerequisite to trust our models, basically, which is really a prerequisite to ask counterfactual questions. And of course that's a very clear link to Aglaé's talk before, where the question in event attribution typically is, what if we would have not changed greenhouse gas emissions in the climate system, or something like that? And in order to do this, we really need the confidence in our models that we can actually, that they are kind of trustworthy in answering these questions. All right, so I wanted to come up with a very simple, with a very simplified detection statement. So in the most simple way that you could imagine, detection now is defined as the process of demonstrating that the climate or a system affected by climate has changed in some defined statistical sense without really providing a reason for that change. So detection, as opposed to attribution, is typically basically a trend assessment, basically showing that there's a trend that is not consistent with internal variability. So you need some understanding of the distribution of internal variability to basically determine whether this trend could be the trend that you're seeing could be a realization of internal variability or whether it's inconsistent with internal variability. So that means detection is more than a statistical trend significance test or so, because you need more than just a statistical test. You need an understanding of internal variability, but it does not go as far as attribution, and it does not claim a certain causality of things. It just says that there is a change that we cannot explain with internal variability. And as an example, you see here 50-year linear temperature trends, and this gray distribution here are all sorts of different 50-year temperature trends from different model simulations without any forced climate change. So this is what the models produce in terms of 50-year trends on a global scale without climate change. And then the black line here is the observations. So in a very simplified sense here, we could claim that the observed trend we see here is over the last 50 years is something like 0.9 degrees temperature increase. And this cannot be consistent with the models, because the models really produce a much narrower distribution. But of course, it requires in some sense, and I'll come back to that point later, it requires in some sense to trust the control distribution of the models in order to do a reasonable job in reproducing variability. Okay, going a step further now, asking what is attribution? So attribution, according to basically IPCC, is defined as, and Aglaé showed a similar plot. Attribution is defined as the process of evaluating the relative contributions of multiple causal factors to a change or to an event within a certain assignment of statistical confidence. So now attribution really goes further than detection in saying that you need to have a causal hypothesis or a causal understanding of what the different drivers are doing. And if you can kind of basically align your hypothesis you have based on your physical understanding with what you're basically analyzing in the observations, then you can claim attribution. And just as an example, so that's a kind of in analogy to the simplified detection example, that's a very simplified attribution as example. So again, taken from the most recent IPCC report. And it basically shows that it says that observed warming from 1850 to 2019 is basically only reproduced in simulations including human influence. So that's the kind of argumentation logic in attribution. So you see in black the observations here basically increasing, and now you see in red, in green, and in blue the three most important sets of causal drivers that are thought to influence the climate. And these are basically greenhouse gas simulations alone. So if one would have only changed the greenhouse gases, then natural causes alone. So natural causes here means solar forcing, and it means volcanic eruptions. So you see some dips here at well-known volcanic eruptions. And the third important factor are aerosol emissions. As I said before, these are cooling the climate. So these are kind of simulations with aerosols only. And if now one assumes that these three are additive, then one arrives at a combined estimate. That's basically the shading in gray here, and that's basically the shading comes from the different climate models. And we see that these observations, they lie well within this combined shading, but they do lie outside of the natural causes alone. So that means, so basically the fact that the observations cannot be explained by natural causes alone, including internal variability, of course, means we have detected the change in a very simplified sense because it's only global mean temperature. But because the observations lie within this gray shading of our known drivers, that means attribution can be claimed here because the observations are consistent with our physical understanding of how basically our physical understanding encapsulated in the climate models, and those climate models then producing these estimates for greenhouse gas and aerosol induced temperature change. So that's the key logic in detection attribution. Maybe I continue a little bit and then I give an opportunity to ask questions again. So detection attribution now is really, I hope to get this point across, is really going from beyond what is actually happening. So beyond making a statistical analysis of what is going on in observations. And it really is about going to why is it happening really. And the IPCC made a kind of a nice figure here that tries to encapsulate the attribution logic. And I would like to go through a little bit through this kind of circle, because that's how most attribution analysis are typically done, including event attribution. But here it's really about trend attribution. So the first step in a detection attribution analysis usually is to identify interesting or relevant questions. So really thinking, what is it I want to look at? Is it interesting scientifically? Is it interesting because it's important for an application or policymakers or so and so forth? And then do some exploratory analysis to understand first, before we're looking at the why, to understand first what is actually going on. So what is going on in terms of trends? Are there other statistical properties that are changing? And also asking questions like, how reliable are my observations? Are there any outliers, biases? Are there missing values? So basically asking, can I really trust the data that I have? But then also really understanding the time scales and the spatial scales of the observations is also an important part initially to really understand what you're dealing with. And then in the second step, and this is again the part where we're going towards the why. So then there needs to be an understanding of the process. So you need to develop in some form an understanding of the time scales and the spatial scales of the signal, or of the thing you think that is a signal, and of the noise. And then you need a quantitative model. And in most cases, this is where existing climate models are invoked in order to say, well, what is actually my hypothesis of the certain different factors that influence the climate? How are they related to the response that I want to attribute? So this is really the logic, that we need a certain hypothesis or physics understanding, and mostly that's encapsulated in a climate model, in order to have this as a hypothesis. And this is also where in the later part of this lecture, probably tomorrow, where these climate models that encapsulate our physical hypothesis are used to build these fingerprints that are then being tested. So the idea is really to make a hypothesis test, but not simply in a statistical sense, but really having a certain physics-based hypothesis at hand, and really only looking for this hypothesis in the data, because we are kind of dealing with a small sample problem here, because we have we don't have so many independent observations in the end. And this is where the actual statistical detection attribution techniques or argumentation comes into play. So then we go towards saying, okay, we apply a certain detection attribution techniques, and when we will look into these techniques tomorrow. We are going to ask, are these observed changes that we're seeing, are they unlikely to be due to internal variability? If this can be shown, again, we can claim detection. If these observed changes are consistent with the calculated responses from these best guess estimates of anthropogenic and natural forcings, such that I've shown in this figure here, then we can claim attribution. And if these observed changes are, but in order to claim attribution, we also must make sure that these observed changes are not consistent with alternative explanation of recent climate. So we must have kind of the best understanding of the relevant drivers at hand. And then as a last thing that we must make sure before we can claim actually attribution is that the difference between the observations and these attribution patterns, so the greenhouse gases and the aerosols and so on, these must be consistent with internal variability. So that's the point I made before, that we must, because we are relying here on the climate models giving us a reasonable estimate of internal variability, we must somehow have a way to evaluate in what way the climate models are realistic in simulating internal variability. And then that's part of the evaluation then in the end, and that's basically the final attribution assessment, then to also understand what are basically the limitations of our theoretical climate model in simulating the signal or variability. So for example, are the spatial scales resolved at which we want to provide an attribution assessment, and what are the limitations of our data and so forth. So this must also be part of the attribution assessment. And I wanted to make a last point about model evaluation. So I've said that internal variability is really important, that's reasonably well simulated by the models, but that's actually still an uncertainty in detection attribution, because this multi-decadal variability is still quite uncertain, and it's highly variable across climate models. So even if we look at the simplified detection statement again, we see that our observations, they lie very far outside of the distribution if all the models are pooled. So all the models basically pooling all the different 50-year unforced trend slopes of climate models, none of them can explain the observed trend. So that means our detection statement is actually quite robust. But at the same time, if we dig a little bit deeper, you see here a histogram of the standard deviation of these 50-year linear trends from individual models. So these are kind of names of individual models, and you see that the number of models that produces a certain value of the standard deviation of 50-year linear trends. We actually see that there's really a large spread in how different climate models reproduce internal variability. And what is a bit worrying is that some of the kind of the most recent climate models are shown in red here, and the slightly older climate models are shown in blue. And at least while of course most models produce a relatively moderate estimate of internal variability on a decadal scale, some of these climate models, some of these newer climate models tend to produce a larger estimate of internal variability. And that's something that really needs to be understood, where these kind of differences in the multi-decadal variability estimates come from. However, having said that, most comparisons, so of course, this model evaluation that's critical for detection attribution, the most comparisons of the models with the observations tend to come to the conclusion that models tend to capture variability in the observations. But of course, as a caveat, the observed record is quite short, so it's quite hard to make in a sense, an apple-to-apple comparison of the variability for timescales of more than several decades or so. So that's a power spectral density plot. So it gives basically the variance of variability on the y-axis against basically the time scale. And of course, if you look at 100-year time scale, it's really hard to estimate variability on 100-year time scales from observations alone, because we have such a short record. And because the short record is a combination of force response and internal variability. So keep in mind that these comparisons are difficult. Okay, so now I wanted to ask if there are any further questions about this more conceptual motivation of detection and attribution. Okay, I don't think so. So I think I have 5 minutes left. And I mean, the first 3 points were the ones that I wanted to cover today. So maybe I can just, if there's no, so that would be a nice opportunity here to discuss more. But if not, then I can just continue a little bit with the introduction into the fingerprinting, and then we would just continue here tomorrow.
Excuse me, I have a question.
Yes, please.
I don't know, just it's like, if I well understood, the detection is more related to the internal variability, and the attribution is related to the understanding of the physical impact of the climate change. And just like to study the detection, just we use statistical model, and for the attribution, also statistical means, and then we try to understand better this physical change. Is that correct?
Yes, that's correct. I mean, I would still also, for detection, I would be careful with only a statistical model, because you need an estimate of internal variability. So you need an estimate of internal variability, and that's usually not derived by statistics alone, but by invoking climate models and simulating this internal variability. But I mean, I definitely agree with what you said, that detection is kind of less critical, because you're not claiming, you're not making a claim about the causal factors. You're simply making the claim of, is there a change that is consistent with the internal variability in the system or not. But the way it's usually framed in IPCC detection attribution is that detection is actually a prerequisite of attribution. So if you want to attribute something, of course you need to detect a change before. I mean, there are some, so kind of the standard way to think about this is that you would do an analysis of some climate quantity, and you would typically first show that there is a change in the system that you cannot explain with internal variability. Then you say, okay, I have detected a change. And then you go on and say, okay, now I want to attribute the change. So I really want to understand the causal factors. And this is then where you go towards attribution. And this is where these physics-based hypotheses about the different factors really come into play and really become important, because there you really want to go all the way and say, well, greenhouse gases, in this case, for example, you would want to say, well, greenhouse gases actually greenhouse gases in isolation would have caused a temperature change of, I don't know, what is that, 1.5 or 1.4 degrees or something like that. But they have been basically compensated by aerosols by minus 0.5 degrees. And that's why we're seeing overall a temperature change of something like 1.1 degrees or so. And these are the statements that you really can only make with attribution, but not with detection.
Okay, thank you. Thank you for good.
Okay, I hope that's clear. And yeah, if there are any other questions, I think we have like a little bit time to discuss.
Oh, yeah, I put my hand up. If there's someone else, please jump in. I think, oh, sorry, go ahead.
Yeah, hi, Professor. Sorry to interrupt you. Like, I have a question. Since we get a power spectral curve for the energy model, so we are getting this spectral curve by the bandpass filter. After getting the signals through the bandpass filters, we are getting the power spectral curve. Now we have the wavelength and the frequency for those climate models by solving those dynamic systems. So by this, can we predict the temperature variable using the frequency by getting the frequency from these spectral curves? Because we have this lambda t equal this Weber model, this Weber equations are there, that lambda parameter and into the t parameter gives some constant, that the Weber equation. So can we just correlate like the thermodynamics equations with the climate change model? We have we can get the frequency from the power spectral curve. Now with these frequencies and with these wavelengths, we can just predict the temperature. Is that feasible, Professor?
Oof. Okay, I must admit I don't really have an answer to that question. Maybe we can continue this discussion later. I mean, maybe Ted has a good answer. I mean, I would be careful with correlations when it comes to detection attribution for the reasons that I've outlined.
Maybe this we could have an offline discussion. Maybe you're talking. I mean, one of the things that, as Sebastian said, when you want to detect, what you normally are asking is whether the observed behavior is consistent with noise, and you have to specify a noise model. As you said, you have to bring in some physical understanding. So there's red noise and different things like that. So I'm not sure if you're referring to something like an energy, energy model where you have a d by dt of the global mean temperature, and you have, of course, various time scales because of the ocean. So there are ways that you would build up a noise model for the power spectrum, which would be your baseline. But I'm not sure if that's what you're on. Maybe let's do that aside. We're almost at the time, but Sebastian, if I may, I just thought it was interesting to raise these conceptual questions. Actually, the previous question, I think, on detection and attribution hit the nail on the head a little bit, because I think the way it's often presented is that the detection is purely a statistical exercise. But as you said, you can't, a noise model needs to be specified, and it's sort of, I think it's something that's not well enough understood, that if you talk about statistical significance, you just can't make a statement like that without qualification. There has to be, you're talking about a chance process, and you have to have a well-defined mathematical definition of that chance process. Otherwise, it's not meaningful. And in some sense, I mean, from a Bayesian point of view, I don't know if you're going to get into Bayesian methods at all, but that's just one of the hypotheses, that's your null hypothesis, and you've got others. And I think the distinction, attribution, I guess, has to, or sorry, detection has to be with looking at the consistency with some sort of statistically stationary chance process or variability. And then attribution will be to do with some non-stationary factor that you bring in, right? I think that's probably the general way to think about it. So I wonder though if you want to comment on that, because I don't think the community is somehow looking at things quite as fundamentally as it potentially could.
Yes, I mean, I absolutely agree with your statements. I mean, the detection has to specify a noise model. And of course, a statistical hypothesis test, in a sense, would also kind of specify some noise model. But I mean, nobody can really verify whether that's the right noise model or not. And so to my mind, it seems more logical to use a noise model that's kind of based in some way on the physics, or to do both. Maybe that could be one way. But I mean, I wanted to bring up these more conceptual things first, because the 2 hours are just not long enough to go into all the depths of the optimal fingerprinting. And so I will present the fingerprinting tomorrow. So there it will be a bit more technical and a bit more hands-on, although not completely still. But exactly, I want to bring these points across, and that's what I hope that you as students would remember from this lecture. So thank you very much for listening, and I look forward to tomorrow.
And if you have questions overnight for either Agle or Sebastian, well, Agle's not there. Yeah, that's right. She's there tomorrow as well. So you can put your questions to tomorrow. Yeah. So thanks everybody, and we take a 2-hour break and come back with Lisa Lloyd at 2 p.m. UK time. All right. Thanks everybody.
Ciao.